which is not necessarily a bad thing. I've done this twice now, taking these 2 hours and squeezing them into 1 hour. It's making me realize that, maybe there wasn't really 2 hours worth of information there. Maybe there was less than that, because there's a lot of stuff I'm throwing away and not missing. Now, I don't think there was really 60 minutes worth of information. I think it's more like 80, but we'll try and squeeze it into 45 or 50 here and see what we can do. It's converting the document right now, 78%. Give it another here. What we're going to talk about is Cobranet, and Cobranet is the other digital network transport besides BlueLink that we support. Cobranet is Ethernet, first of all, whereas BlueLink is not. BlueLink uses Ethernet PHYs and uses some Ethernet technology to make itself work, but it's not, technically speaking, Ethernet. You can't put it through switches, that sort of thing. Whereas Cobranet is real live Ethernet. There's your full screen button. My skip ahead button. There we go. And Cobranet transmits audio using what are called bundles. And inside the CM1 module, by the way, you're going to hear me refer to this over and over again. The CM1 module is a circuit board. It's about not quite twice as big as a playing card. Be 1.5 times as wide as a playing card. It's a little circuit board that actually sockets into motherboard of the Blue 80 or Blue 800 or Blue 32, whatever. When I say Blue 80, I mean generically the 80, 32, 800, and 320. They all have the same chips or the same sockets for the CM1. They all use the same CM1 module. So that's just generically any of them. The CM1 module sockets in there. It's a separate device. The Blue 80 hands the CM1 module control information and digital audio. CM1 takes that digital audio and puts it into bundles and puts them on the network. And each CM1 can handle or process up to 4 outgoing bundles, up to 4 incoming bundles, all at one time. How many channels are in a bundle? Well, usually it's 8 channels. In most cases, it's 8. If you switch to 96, then it's usually 4. 96K sample rate. It's usually 4 channels in a bundle. And those are just the standard what fits in a bundle. There are some exceptions to that. If you start monkeying around with 24-bit data streams, or you start monkeying around with different latency settings, you can end up with fewer channels. A good rule of thumb, it's 8 and 4. And let an architect will tell you if that changes. So we've got 4 bundles coming out of the CM1 module, each with potentially 8 channels on it, which is 32 channels coming out and 32 channels going in. But how many channels can we have total across our network? Hope I skipped ahead, actually. Let's back up. The bundles. There are 2 different types of bundles, a multicast bundle and a unicast bundle. And the only difference between the 2 is what you tell it to do. If you have a bundle of audio that you want transmitted to every device on the network, that's called a multicast bundle. And the way to tell the CM1 module you want this bundle multicast, you just give it a number between 1 and 255. Every bundle has a number. That number is the unique identifier for that bundle. Here's bundle number 47. Here's bundle number 618. And if you number it, a number from 1 to 255, the CM1 module will know automatically, oh, okay, this one is a multicast bundle. That means I spam it out to everybody, no matter what. And I mean everybody, not every Cobranet device, but every device on the network receives it. No matter what kind of device it is, it goes everywhere. On the other hand, if you only want your bundle to go to one destination, then you make it a unicast bundle. And that's done just by giving a number, 256 or above. So if I take 8 channels of audio and I hand it to the CM1 module and I say, here's bundle 300, the CM1 module is going to hold that bundle, do nothing with it until somebody requests it. It's an important bit of information. Multicast bundles leave the device immediately upon creation. They're transmitted automatically right now. Here we go. Unicast bundles are transmitted only when another device requests it. With Cobranet, you don't assign bundles to go places. You request them to come to the receiving device. So now comes the question that I tried to skip ahead to before. How many bundles can you have on your network without overloading your Ethernet network? Well, technically 65,000 of them, because you have 65,000 numbers you can use. Now, the number of bundles per connection is limited to 8. What's a connection? A connection, and the way I think about it, is a connection is one cable by network. In reality, the limiting factor a connection is the network transmitting port on the switch or on the device. That's what limits it to only 8 bundles. But in terms of designing the network and dealing with the real world type of stuff we have to deal with, I just think about it as one cable. One 100 base T cable can carry 8 bundles in each direction. Simple enough. Because a bundle is effectively 12 megabits. Okay. 8 times 12 is 96. That fits in 100. 9 times 12 is 108. That doesn't fit so well in 100. Pretty straightforward and simple stuff. 8 bundles per connection, which is effectively a cable. What that means is you have to watch out once in a while. Take this up to full screen mode for myself so I can scriggle on this and make it legible. In this example, I've got a scribble board. I've got 3 devices up here in the south building, master control room, tied into a bunch of satellite receivers for satellite music, do my background music, and I'm shipping those across the network as multicast bundles. So everybody can get the background music if they want. Okay? That means that each one of these devices that has 16 inputs, 8 channels per bundle, that means each one of these devices is transmitting 2 bundles. 2 multicast bundles coming out here, 2 coming out here, there's 2 coming out here. That means that those 6 multicast bundles are going into every device in the network. 6 bundles coming into each one of these. There's 6 bundles going into each one of the north building devices. Now, in addition to that, I also have some devices down here in the south building that are transmitting only to the north building. South number 1 transmits only to north number 1. South 2 only to north 2. South 3 only to north 3. Oh, didn't mean to do that. Put that back. Nope. So what do I have there as far as traffic? Well, I've got a single Cobranet bundle coming out of each one of these south devices and going into each one of the north devices, in addition to my big googly pile of multicast bundles. So what's being carried by each one of these cables right over here? Each one of those cables is carrying 6 multicast and 1 unicast for a total of 7. The max of 8. Problem. Rock and roll. Works great. Now, what happens if somebody comes along and decides they want to save some money and time on pulling cable between your 2 buildings here, and they're going to just stick a switch in the second building? Save some cable. What happens to our network? Well, this cable in the middle between the 2 buildings, it's now carrying 6 multicast bundles that it's always been carrying. Every cable in the system carries. But in addition, this cable is also bringing 3 unicast bundles from south to north for a total of 9. Now I have 9 bundles of that cable. It's going to overload. Can't handle it. Too much data. So in that situation, We need to keep track of our bundle counts, make sure we don't overload the system. Now, how do you resolve that problem? What do you do if you get in that situation? Well, it depends on the type of switch you bought, and I'll talk a little more about which switches to buy in a bit. But if you have the right switch, you can just throw a second Cat5 in there. It'll span across the two Cat5s for you. If you don't have that type of switch, then you might have to go to a fiber converter or a gigabit converter. Not a fiber converter, but a gigabit converter. Do a gigabit connection between those two devices. Get the additional bandwidth you need. Because if you change this over to a gigabit connection, you've got 10 times the bandwidth. Plenty of space for those 9 bundles to cruise through. That's why it's important to keep track of how many bundles you have. Any questions on that so far? Okay. In each Cobranet network, there's a Cobranet conductor. And the conductor does master clock and something called bundle transmission arbitration. Bundle transmission arbitration means when BlueA number 1 goes online, it has bundle 300 ready to transmit. There an orange line through my screen. There you go. It sends what's called a reservation packet to the conductor, telling the conductor, I have bundle 300 ready to transmit, and then it sits and waits. Every 1.3 milliseconds, the conductor spits out a beat packet. It's your timing packet. The beat packet also carries a list embedded inside of it of every device on the network that's allowed to transmit, what it's supposed to transmit, who it's supposed to transmit it to. So when the BlueA number 2 comes online, it sends a reservation packet to the conductor saying, I have bundle number 300 I'd like to receive, please. The conductor on the next beat packet includes a line telling device 1 transmit bundle 300 to device 2, giving it the correct MAC address and that kind of stuff. Right? That's the conductor doing that. Until the conductor says so, BlueA number 1 will not transmit. Now, number 1 might be the conductor too, doesn't matter. Until it's in the beat packet, it won't transmit. You can change the transmit priority. If you have 2 devices, both with the same bundle, a different transmit priority, right here in properties, you can change that priority. And what that means is, device number 1 comes online and says, I have bundle 300 priority of 24. Device 2 says, I'm ready to receive bundle 300. Device 3 says, I have bundle 300 priority of 30. Conductor, in the next beat packet, will tell device number 3 transmit to device number 2 because device number 3 has the higher priority. Device number 2 will not receive any instructions. It'll check the beat packet. It's not mentioned. Okay, I just sit here and do nothing. As soon as number 3 is removed from the system or disconnected, the very next beat packet will tell device 1, start transmitting. Transmit to device number 2. Does that make sense, everybody? Bundle transmission arbitration. It's not terribly important you really even know that stuff, but it's just good to know what's going on under the hood, why it works the way it does. Question came up, can you multicast on 4 channels and unicast on 4 channels of one bundle? No. Every bundle has a number. That number determines whether that bundle is multicast or unicast. Every bundle has exactly one number. Therefore, every bundle is either multicast or unicast. There's no way to mix and match them. Can't mix and match them. It is possible to change your conductor priority if you want to control who's the conductor. Generally speaking, don't. Leave it alone. There's really no reason to mess with it. The only time you ever have to worry about it is if you happen to have a system where some of the devices are routinely powered off. Both are going to be powered off, and you don't want them to be the conductor. If that's the case, contact us. We'll tech support, and we'll talk you through figuring out which one is the best one to use for a conductor. Because there are a couple different considerations there. The most important one being it's got to be something who's going to be turned on 24/7. But other than that, not a big deal. Or at least, I shouldn't say 24/7. It's going to be somebody's turned on anytime the system is turned on. But other than that, it's not a real big deal. The CM1 module we talked about before that does the actual Cobranet, that's what I'm looking for, Cobranet encoding and decoding, has basically 3 properties. Has sample rate, which would be 48K or 96K, and that is set by the Blue 80. There is no way to set it directly on the CM1 card. Set the Blue 80 to either 48K or 96K, and it sets the CM1 card to match because it must match, not optional. CM1 is set to 48K. That's because the Blue 80 is set to 48K. It has to be that way. There are other software packages like the Discovery tool from Cobranet, for instance, which will allow you to go in and override that, change it to 96K when the Blue 80 is still set to 48K. I'm going to go ahead and just be blatantly honest with you. As soon as we hang the phone up, we will laugh at you after that tech support phone call. Let's be honest. Do not ever use any software except London Architect to do anything with London Box or any part of it. Not use the Discovery tool to dink around with the CM1 module. Not use the utility that comes with the Yamaha consoles to fool around with the CM1 module. It's not going to be a good thing. There are a whole bunch of things you can reconfigure about the CM1 module using those tools, and I'm going to say ballparking it 3/4 of those things. If you change them, the Blue 80 will stop talking to that CM1 module, and there's nothing you can do about it except hope you can remember the default value and set it back. Guess what? I don't know the default values of all those things. We never monkey with them. So if you do goof it up, it's going to be several days potentially before we can get you an answer on what the default values are. Because first I've got to send an email to the engineers. I'll wait for the engineers to reply. Then I got to send an email back to you as to what the heck those values are. So don't mess around with any other software. You can also change the bit depth. Bit depth, there's almost no rules really. You can mix and match them however you want. You can have, channels 1, 2, and 3 are all 16-bit, 4 and 5 are 20-bit, 6 is 24, and 7 and 8 are back to 20. Doesn't matter. Receiving device just picks up whatever bit depth the transmitting device is set. Latency, there are 3 levels of latency, 5.3, 2.6, or 1.3. You should always use 5.3. 2.6 and 1.3 are marketing hype. There's no valid reason to use them in 99.99999% of all situations. If you'd like to give me a call or an email with your specific situation, I can tell you exactly why it doesn't matter in your situation. But what it comes down to is, in your system, in your network, you're going to have, where's my little slide? You're going to have an overall total latency based on 4 things. A to D conversion takes time, D to A conversion takes time, Cobranet takes time, and processing objects take time. Processing objects I've left blank on here because processing objects are measured in microseconds. So it's like, who cares? If you get a crazy line file, it might be 300 or 400 microseconds, which is 0.3 milliseconds or 0.4 milliseconds. Like, why worry about it? Okay, so here's our total latencies. To me, those make a little more sense for me to think about if I switch over to feet and inches. Talk about it as feet and inches. That's how far sound travels that amount of time. There are 3 scenarios with regard to latency in our world. The first scenario is you have the latent signal and the non-latent signal, and you're mixing them back together somehow. In that situation, if you use low latency, your total latency is 2.26 milliseconds. Total difference is 2.26 milliseconds. Are you allowed to ignore that 2.26 milliseconds because it's only 2.26? No. You got to slap a delay in there and time align your 2 channels or your 2 signals. If you've chosen 5.3 for Cobranet, your total is 6.26 milliseconds. Does that make a difference? No, absolutely no difference. You still have to slap a delay in there. You can type in 6.26 instead of 2.26, or 5.3 instead of 1.3. It's done. So in both cases, you must compensate. It's not optional. You just change the number. Okay, so in that situation, there's no advantage to 1.3 milliseconds versus 5.3 milliseconds. Second possible scenario is where you have just the latent signal only. Best example of that is from front of house to your drive rack or drive packs hanging in the ceiling. Run Cobranet from front of house up to the drive packs. All right. Well, if I set for 1.3 versus 5.3, is a difference of 4 milliseconds. My total latency. What does that difference mean to me? Do I care about it? Does it matter? That 4 millisecond difference is the equivalent of taking your speakers and pushing them upstage by about 4.5 feet. That's it. That's the total psychoacoustic effect of that 4 milliseconds. Push it upstage by 4.5 feet. Now, if you hung your speakers in the mathematically precise location where they must be, this facility, then that's fine. If, however, you hung your speakers off the pick point, off the structural steel where it was, then you have no reason to worry about that 4 milliseconds. So unless your speakers have to be in that exact position, 4 milliseconds doesn't matter. There's only one example I've ever seen in my entire life where a speaker had to be exactly where it was placed. That's an 18-inch speaker in a church in, I can't remember where in the heck this church is located, but that speaker is actually used to do low-frequency reinforcement for the pipe organ. And we're talking low frequency. We're talking like, 26 hertz and down. Because of that, the distance between the mouth of the lowest pipes on the organ and the cone of that speaker had to be exactly one wavelength at a certain frequency. Otherwise, you get cancellation. So in that situation, you have to have that speaker in exactly the right spot, right? Except you don't. Even in that example, if we knew that we had an extra 4 milliseconds of latency, all we have to do is take that speaker and move it forward 4.5 feet further away from the pipes. We're done. We fixed it. So if your speakers are mathematically precisely aligned to something and you're not allowed to move them, then that delay of 4 milliseconds might make a difference. Unlikely you'll ever experience that. Third scenario, you have the sound coming out of the speakers. It's now a mechanical wave. We can now say the word Haas effect without getting giggled at, because there is no Haas effect inside of a device. It only exists in a free air mechanical wave system. And we have the stage volume versus the sound coming out of the speakers. The sound coming out of the speakers is latent. Stage volume could be a number of things. It could be the snare drum in the orchestra. It could be the guitar player's 14 stacks at 8,000 watts apiece. It could be the opera singer, because opera singers can make every bit as much noise as any Marshall cabinet ever built, believe it or not. It's not uncommon at all for professional opera singers to break 126 to 128 dB at their mouth. That's kind of scary. It's kind of frightening to think about it. We got the sound coming off the stage and the sound coming out of the speakers, and they're not matched. What do? Well, in this situation where we're going to want to use Haas effect, make it sound like the sound's all coming off the stage, right? So we have to add delay to our speakers, push them back, time align them properly. So we're going to take either that 1.3 or the 5.3 and add more delay to it. Does it matter which one we set for? No. No benefit to the 1.3. It's going to add more delay. So you can see that you don't gain anything, no benefit to using 1.3 milliseconds of latency. So what's the negative? What do you lose? Negative is Peak Audio, who invented Cobranet, says that you should not have more than 7 switch hops between 2 Cobranet devices. What the heck's a switch hop? Right there on the screen is 1 and 4 to give you an idea what they look like. Basically, every time you go through a switch, it's a hop. And that's because in the switch, you have two things. You have a lookup table, which takes a little bit of time. And switches are also what's called a store and forward device, meaning the entire data packet must arrive, must be checksummed, and then they can start transmitting it. That slows that data packet down just a touch. Not a huge amount of time, but it does add up eventually. And if you have more than 7 hops, or if you have 8 hops, you've exceeded the 5.3 milliseconds of the buffer. That's what that 5.3 milliseconds of latency is. It's a receive buffer. It's not a side effect or an after effect. It's what makes Cobranet work. If you go to 2.26 milliseconds, you've cut the buffer in half. If you go to 1.3, you've cut it down to a quarter. At at 5.3 milliseconds latency, 8 hops is too many. Right? You start having problems in your network. If you cut that down to 2.6 milliseconds, 4 hops is too many. Cut that down to 1.3, 2 hops is too many. At 1.3 milliseconds latency, every single device in the network has to be plugged into the same switch. One switch. If you're using fully gigabit switches, it may be possible to have up to 3 switches at 1.3 milliseconds latency, but what's the point? Remember, we're gaining nothing, and now, to make it work, we have to buy these Mongo huge enterprise quality switches. They're going to cost us a couple $1,000 instead of buying the $400 switch we should have bought. So low latency, a bad thing, not a good thing. It's going to just do horrible, mean things to your network and not gain you anything. Now bear in mind all these hop restrictions, that kind of stuff, that all has to do with Cobranet, not IQNet. Nothing to do with your control data, just the Cobranet data. Okay? Any questions on Cobranet? Oh, I went kind of quick through that, but it's just the basics, how it works. All right. The other side of this big dog is building a network. And whether you're talking about the Cobranet or the IQNet, you got to build a network for it. And all networks are based on stars. Whether we're talking about your home office or the internet, every network is a star. And those stars, each green dot in this illustration is a star. We could tie those stars together and form more complex networks. Star of stars? It's the simplest thing to do, but it's a pretty lousy network. Because if that center switch goes down, the whole thing falls apart. Ring of stars is a great network. Fantastic topology. Very fault tolerant. If any one thing goes down, everybody can still talk to everybody else. The only thing is, if you're going to do a ring network, a ring topology, you have to make sure you buy the right switches. Because to do a ring, you must buy switches that are capable of spanning. You have to be capable of spanning protocol to form a ring. Now, in reality, what we usually end up with is a mesh. Sometimes a mess, but usually a mesh. A mesh is a ring with something hanging off the outside of it, or a ring with some cross connects inside of it. Any ring that's been modified slightly is a mesh. If you want to do a mesh, you have to have a switch capable of spanning, because it's got a ring, and meshing, because it has other stuff. Other stuff being a technical term. Why did my little underlines just go away and change themselves? That's creeping me out, guys. Why is my underline going away by itself? I'm not doing that. Interesting. Sure, what's going on here? That one's still there. Where's the ones over? Okay. Spanning. Meshing. Now behave. Okay, so do a mesh means spanning and meshing protocol. When I design a network and spec a switch, I always get a switch capable of spanning and meshing. Always. Because they're not that expensive anymore. It used to be kind of an expensive thing to get the nicer switches with spanning and meshing on them. Nowadays, it's no big deal. If you get spanning and meshing and don't need it, so what? It costs you an extra $50 or $100. No big deal. If you don't get it and you need it, now you're in the soup. Because you can't get away without it. Okay? So you want spanning and meshing. You should never use a hub for Cobranet. I guess technically you could use a hub for IQNet, but I wouldn't. It's going to be horrible. It just does terrible things to your data bandwidth, your network bandwidth. You always want to buy a switch. Switches are full duplex, which means you can transmit and receive both at the same time, and they send data only to where it's supposed to go instead of spamming it out every place. And specifically, the switch you want to buy should be non-blocking for Cobranet. Non-blocking means transmit and receive on every port all at the same time and not get overloaded. So we need spanning, meshing, and non-blocking. And we need to make sure we don't accidentally buy a router. Routers are really cool for certain things, but routers block Cobranet. There's no way to get Cobranet through a router. Can't be done. Routers also block IQNet broadcast messages. So if London Architect is on one side of the router and the blue box is on the other side of the router, London Architect won't see them. Now there's ways around that. We can do a configuration that will fix that using static routes, or if you're outside the US, static routes. But that requires some configuration. You have to know you've got a router. So make sure you don't get a router by accident. You want a switch, you want spanning, you want meshing, and you want non-blocking. Does that make sense, everybody? If you're in the US, you can kind of equate that to about $20 a port, more or less. That's a good ballpark number. If you're doing a budget and you want to be really, really safe, if I'm doing a budget and I want to be really safe about it, I always say $25 a port. I guarantee I can find a switch that will do the job just fine for $25 a port. Work great. Spanning, meshing, and non-blocking switches. That's what you got to have. No questions? Okay. See, what's with the little lines showing up again all of a sudden? Can you guys see those? Yeah, I can see them on a monitor computer. It's funny. I'll make them go away. It's kind of creeping me out. Let's talk about redundancy for a few minutes. There's a lot of different forms of redundancy. If you're worried about this cable backing out on you, you can always put in a second cable, as long as you have spanning, because now it's a circle, right? We made a loop after spanning. If you're worried about this cable right here cacking out, put in secondary Cobranet. Now, it's tempting to think to ourselves, wait a minute, this cable right here, it's a foot long. It's in the rack. How can it go bad? Well, it's not always. I just did a project at a private school, where they had 2 worship spaces with this outdoor patio between them. Each worship space had 3 classrooms hanging off it going to the north, or to the south, I mean. So your 2 worship spaces, east and west, and classrooms down to the south. All the classrooms and the worship space on the east side were fed signals from a single Blue 32. On the west side, you had a Blue 80, a Blue 32, and all the sources and stuff. On the east side, just the one Blue 32. So they're only, maybe 65 yards apart at most, with all the right angles in the conduit. So they just put a single switch on the west side and ran cable over from the switch to the east side for that single Blue 32. That's a great example of when you might want to use secondary Cobranet, because my orange line changed, because the secondary Cobranet allows you to have redundancy for that 65-yard long cable. Now, what is secondary Cobranet? Go back here real quick. This illustration. Secondary Cobranet, there are a pair of ports right here labeled primary and secondary. See where that, change the color of that line so we can tell when it shows up later it came from this page. That'd be fun. It's like, where's Waldo? There you go, primary and secondary. How do they work? Well, the CM1 module will always transmit and receive on the primary port as long as there's anything plugged into the primary port. Anything at all. Switch, hub, router, another computer, whatever. If there's some Ethernet device out there, it'll use the primary port. If there's no Ethernet device attached to the primary, but there is attached to the secondary, then it'll use the secondary instead. What that means for us is, let's say we want to design a network to deal with the possibility that we might lose this switch. If we're worried about that switch dying, what do? Well, here's a network that won't work. Because if this switch dies, what's going to happen to our audio signal? The north building is going to stop using primary and start using secondary, which means it's going to come down here into this switch. It's going to come over here, cruise down to this switch. It's going to go over here, cruise down. It's come over here, and it's going to get ignored because the south building still has a good switch on the primary. Now, luckily, it's easy to fix. Just cross-connect your two switches, you're done. Problem solved. Now you have a redundant data path everywhere you want to go. If this device fails, we can pop in a second device with a lower transmit priority. We talked about transmit priority earlier. A little tip for you, if you ever do this, I actually don't use different transmit priorities. I rely on a feature in Cobranet instead, which is that if two devices come online, both with the same bundle and the same transmit priority, what's Cobranet going to do? Is it going to just curl up its toes and die? Well, no, that's not very useful. So what it does is whichever one of them booted up first is allowed to transmit. Now, why is that useful to us? Let's pretend the one on the left has a transmit priority of 3. One on the right has a transmit priority of 2. What happens if something goofs up in the north number 1, priority of 3, that causes that device to reboot every 60 seconds? Well, it's going to reboot and go away. Backup's going to take over. Primary is going to come back and take over again from the backup, and then reboot itself. Rinse and repeat over and over again. And so you're going to get these constant interruptions to your audio as that device reboots itself over and over again. If you just set them both with the same transmit priority, whichever one comes up first becomes the transmitter. The other one becomes the backup. And if the transmitting device does crash, backup takes over, but when the primary comes back, it does not get the transmit back. Backup keeps transmitting. So if you get one of those cyclical errors, you won't get a problem where the audio keeps cutting in and out. Now, obviously, in that case, you better be careful and make up a control panel. It'll tell you which device is transmitting, which one's not, because otherwise, you could have a failure and never notice it. That's a common theme throughout redundancy. You could have a failure and not realize you had a failure. So make sure you have some way to check it. On receive redundancy, there's a thing called buddy link that doesn't work all that well. Don't use it for life safety, whatever you do. There is a way to set up receive redundancy. We're not going to spend a lot of time on it. If you ever need to do it, give me a call. I'll walk you through it. Okay. Scroll down here real quick. What's that? Oh, that's that. That's that. Don't worry about that. I can worry about that. All right. Wireless Cobranet. Last thing we'll talk about real quick is wireless Cobranet. It works sometimes if you do it right. Basically, if you want to do wireless Cobranet and you're thinking of RF wireless, like 802.11, not going to work. Just will not work. First of all wireless access points contain routers, by definition. Routers won't pass Cobranet. Problem. Second of all, most wireless access points can't handle the bandwidth of Cobranet. Even though they're supposedly a 100 base T device, they can't really cope with that much data. And so they fall over dead. The device called a bridge, which may work to transfer Cobranet data over radio, RF. I say may because a bridge has no router in it. A bridge is kind of a dumb device, kind of like the gigabit Ethernet fiber converter we talked about. A bridge just takes in ones and zeros and puts them on the radio and spits them out, sends them off to the other side. It doesn't care what those ones and zeros mean. It's just all ones and zeros. Okay? So if a bridge is truly a bridge and just taking in ones and zeros, then yes, Cobranet could pass through it, or will pass through it, I should say. However, about half the bridges out there, quote-unquote bridge, you find, when you go surfing the web looking to buy an Ethernet bridge, what you actually get is a wireless access point with different firmware. And it still won't handle the bandwidth. Ballpark numbers that I found, bridges that will survive Cobranet run about $1,200 to $1,400 a piece. So if you find yourself a bargain basement bridge for $300, it probably won't work. Go ahead and buy it and try it out. Make sure you can return it. The infrared laser connections work perfectly. They work great. Get those from a lot of companies in the IT industry. One company in our industry makes them. They work fantastic. Wireless Cobranet. Wireless control is almost the exact opposite. Wireless control is nothing. It's a piece of cake. There's nothing to it. If you can configure your wireless access points so you can surf the web, you're done. Go into London Architect, you click on Tools, Application Preferences, hit the HiQNet tab. That's where you pick which network interface card you want to use. Because like my laptop has 3 different network interface cards. Technically, it's got the gigabit Ethernet card, it's got the wireless card, it's got this funky infrared thing that it pretends is a NIC. I'm not sure why. But to pick between those 3. If I'm running a VPN, there's a 4th one to pick from. If I pick the wired adapter, I'm connected wired. If I pick the wireless adapter, I'm connected and controlling wirelessly. That's all there is to it. Absolutely all there is to it. So, Cobranet wireless can be done. It's not necessarily easy. Control wireless, piece of cake, nothing to it. Questions on that? Full screen button still there? Yeah, it is. Nobody has a question? All right. It looks to me like Chicago time. It's not quite 2 o'clock, so we'll go ahead and pretend it's really 2, and we'll take a break until 10 after 2. If you come up with any questions between now and then, go ahead and type them in. I'll answer them after the break. See you guys in 10 minutes.